So for this example here, this is going to be another two-dimensional question, but this one's going to be a little bit trickier because it's going to try to attack a common misconception students have about the normal force whenever we're on a flat surface. So let's look at what we have going on here. So on a hot sunny day, I myself am going to do some yard work, and it might be a little bit on the fictional side. So I'm going to be pushing this lawnmower with a mass of 50 kilos. So I'm also going to apply a force of 400 newtons, and I'm going to do that 40 degrees below the horizontal on a lawnmower handle such that it moves with constant velocity. So before we get to anything, that word constant velocity, we want to have those alarm bells going off in our head, because as soon as we see constant velocity, we want to write down the net force is 0. That's really important. So we're being asked a few things. We want to find the components of the applied force acting on the lawnmower, certainly important. We want to determine the magnitude of the force of friction between the grass and the lawnmower, and we're going to determine the normal force. All right, a lot going on in here. First thing though, let's draw a free body diagram. So I'm going to have my free body diagram. Now I am going to say, let's say I'm pushing this lawnmower, let's say I'm pushing it to the left. Pushing left. Because why not? So if I'm pushing this thing to the left, now my applied force, first of all, it's 40 degrees below the horizontal. Now a lot of people, they'd want to draw the vector pointing down and pointing into the free body diagram's dot. Almost. We want to just translate that vector because we want the tail of that vector. We want the tail of that vector to be coming from the free body diagram's dot. So that vector, the applied force, it's going to look a little bit something like this instead. So we're going to have that applied force, and then this angle here is going to be 40 degrees below the horizontal. I'll sketch that in a moment. Now, we are told that this moves with constant velocity. Well, if it's moving with constant velocity, if I have an applied force that's pushing it forward, something has to be slowing it down, which is going to be the force of friction. But this is where you have to be careful. The lawnmower is moving on a flat surface, so it's moving in the left direction. What this means is that my force of friction has to be going to the right. The force of friction is actually only going to oppose my horizontal motion, just because this lawnmower is moving horizontally. So it's not going to be directly opposite to FA, it's only going to be opposite to the X component. And we will sketch in the components of this soon enough. So now, my lawnmower, it is going to have a normal force and a force of gravity. So I'm going to have a force of gravity here, however long it happens to be. We're going to have a normal force. I'll make it like this. Maybe I'll make that force of gravity just a smidge longer, just because I can. Now, that's the free body diagram, but most likely because the applied force, it kind of sticks out like a sore thumb here. It's the only one that's not in the X or Y direction. So what we should probably do is get its components that are going in those directions. So I'm going to have this component of the applied force in the X direction here. And I'm also going to have this component of the applied force in the Y direction here. So that angle here between this horizontal and this FA, that's our 40 degrees. So this is our free body diagram. Now, what we want to do is we want to sketch, we want to decide what's going to be positive. So for this, I am going to say, we're going to say to the left and up, those are going to be our positive conventions. So first thing first, let's break down the component of the applied force. So whenever I break down a vector, I always like to sketch the vector. So here is my lovely vector. That's my applied force. And then I also like to sketch in the components of it. So here is my X component, and here is my Y component. And then we also have that angle of 40 degrees. Now for this, I know the applied force. We know that this vector is 400 newtons. What I'm interested in is finding my X and Y components. Well, looking at this triangle, the 400 newtons is going to be my hypotenuse. The Y component is going to be my opposite. FAX is going to be my adjacent, since I'm using my adjacent and my hypotenuse to get FAX. we're going to need cosine. So FAX is going to be that applied force times cos of my angle. So I have my 400 newtons times cos of 40 degrees. Again, we're doing trig. Do not forget to put your calculator in degree mode. So this is going to be about 306.42 newtons. And then for the y component, we're just going to use the sine. So this time we're going to have FA times sine of the angle, which again is our lovely 400 newtons times sine of 40 degrees, which is going to give me, let's see here, about 257.11 newtons. Again, sig digs are not my concern right now. The only thing, let's just check very quickly here. Now, my FAX is pointing to the left. We have called left positive. We can leave the sign B on there. Just like when we did stuff in kinematics though, we got to watch our signs here on our components. So FAY, its component is pointing down, but I've called up positive. I have to put a negative on FAY because it points down. And that's really important. It'd be great if I had a pen that worked, but let's try that again. Points down. So watch that when you're breaking down components. Check the directions where the components are pointing and check that against your positive convention. Because if we miss that sign there, that's going to mess things up critically. Right. So we have our components. We're just doing this first because that takes away a lot of the legwork. Because we're likely going to need those components anyways. Now we have them here. Now we can access them really quickly. So part B has asked us to look at the magnitude of the force of friction between the grass and the lawnmower. The force of friction is acting in the horizontal direction. So if it's acting in the horizontal direction, let's look at horizontal forces, or horizontal direction. So my net force horizontally, so I'll just say the net force in the x direction, it's going to be this applied force in the x direction, so that FAX, not FA, the component of the x component of FA, plus that force of friction. Well, the other thing, as I asked you to hint at earlier, or to be mindful of, constant velocity, net force is 0, so this piece is going away. So we're going to have 0 equals FAX plus FF. So what this is going to tell us is that the force of friction is going to be the negative of the opponent. Oh my goodness, I can't speak. The force of friction is going to be the negative of the x component of the applied force. So because this thing's moving at constant velocity, those two pieces have to balance each other out. Well, we've already found this. We found it's about, it's about 306.42 newtons. Now, the negative here is just telling us the direction of the force of friction. We have called left positive. The negative is telling us that the force of friction is going right. So that's good. Our answer, the sign of our answer is consistent with our free body diagram. But since we only want magnitude, we don't care about direction, we don't care about the negative sign. So then I could just say the magnitude of my force of friction. We'll say it's about 306 newtons to respect significant digits. So that wasn't too bad. Part C is the one that's a little bit trickier, and this is where I'll show you what's going on. So this time we're looking at the normal force. The normal force resides in my vertical direction. So this time we're going to have an examination of just the vertical or the y direction. So the vertical direction, what do we got going on here? Well, the net force in my y direction, let's have a look. In the vertical plane, I have three things. I have my normal force, I have my force of gravity, but I also have this little scraggler tagging along this time. I have this applied force, the y component of this applied force. So I actually have three pieces here. So I have the normal force plus Fg plus Fay. And that's where we have to be careful. We can't forget this component of the applied force. Because think of it, when you're pushing that lawnmower at an angle, part of you is pushing it horizontally, but part of you is also pushing it into the ground too. The normal force has to counteract that force of gravity and that piece, that component of the force that you're pushing into the ground. So we can't forget that. You are supplying this. Now again, constant velocity, that tells us net force is going to take a hike. So we do not need that term. So we're going to have Fn plus Fg plus Fay. All right, well, the normal force here, the normal force on this is going to be the negative of the force of gravity minus the applied force. Okay, so we got a lot of those negatives in there. And of course, we know Fg is just mg. And then we got the negative of Fay. As everything we've done with vectors, be careful with the signs. So my normal force, I have that negative. My mass is 50 kilos. Now, G is going to point down, and we have called up positive. So G is going to have to go in as a negative 9.81 meters per second squared. And then we're going to subtract off our component, the y component of our applied force. But again, because it's pointing down, we had to put that negative in there. So we're going to be subtracting off negative 257.11 newtons. So as everything with all this stuff in dynamics, kinematics, anytime we're dealing with vectors, the free body diagram is going to save you a lot of trouble. But also at the same time, you have to be really careful with your signs, because a missed negative sign here and there, that can affect your answer. So be really careful. But the other advice I'd give you for that too is take your time on these problems. There's absolutely no reason to rush them. Questions like these on quizzes, exams, they're going to be worth a lot of marks because there's going to be a lot of steps. If it's worth a lot of marks, we expect you to take your time. Don't rush it. So for this, I'm going to get about 747.62. So I've been asked to determine the normal force. So the normal force on this thing, it's going to be about 748 newtons. Now, I probably should have find the magnitude of the normal force, but I didn't do that, so I have to put a direction. Well, there's not a lot of guidance for the direction here, so how about I just say it's 748 newtons up? Because then I have my magnitude, and then I have my direction. The trap on this one is we're so used to flat surfaces, we're used to saying, oh, the normal force is equal to the force of gravity. Yeah, if there's no applied force pushing into the ground, you're more than correct on that. But because in this case, we're pushing that lawnmower into the ground as well as horizontally, the normal force has to also counteract that bit we're pushing into the ground along with the force of gravity. So as I've mentioned, a free body diagram, it's going to save you a lot of trouble. So make sure you're drawing them for every single question involving forces.